Dr. Y. Sarada, Professor, Department of Mathematics, Anna University. Her area of specialization is applied probability and stochastic modeling. She has about 25 research publications in national and international journals. She has guided students for research projects. She has delivered lectures in her area of specialization in many institutions.
Welcome to the UGC lecture series on queuing and reliability. Presently, we are looking into the queuing models. In the last lecture, we started with the infinite server model, where every customer, he or she, is her or his own server. The self-service models in general are called so because of each customer being his or her own server. For example, taking the license test of a person is considered to be a self-service. So, this model, this situation can be modeled as a self-service model. Also, it is possible that the ATM service and also the 24-hour banks and the self-service gas stations, these situations can also be considered as the self-service queuing model, but then here actually the servers are the computers, and hence these cannot be considered as examples of self-service model, because the customer only operates the computer in a ATM counter. So, this example cannot be considered as an example for the infinite server Markovian queuing model. So, let us look into what we did in the last lecture. I had asked you to compute the probability P naught. Let us see that now. So, the infinite server model MM infinity GD infinity infinity is the Kendall's notation. Lambda n is equal to lambda, n equal to 0, 1, 2, 3 etc. Mu n equal to n into mu, n equal to 1, 2, 3 and so on. In this case, the service rate increases with increase in the queue length, and hence it is known as a queuing problem with infinite number of channels or servers. Also, we started with the generalized Poisson queuing model here and substituted the lambda n's and mu n's into the expression for P n, the steady state probability of finding n customers in the system. So, we consider the P n in the generalized Poisson queuing model, which is given by lambda naught into lambda 1 into lambda 2 and so on, lambda n minus 1 divided by mu 1, mu 2, mu 3 and so on mu n into P naught, where P n, when you substitute for lambdas and mu's, is going to be lambda written product n times in the numerator and denominator 1 into mu, 2 into mu and so on up to n mu, which when you pull out the mu's out will give you mu power n in the denominator. Already lambda power n will be there in the numerator, n factorial separates out in the denominator. So, we have P n equal to rho power n, because rho is defined as lambda by mu by n factorial into P naught, and n takes the value 0, 1, 2, 3 etc. So, to find P naught we use the normalizing condition sigma n equal to 0 to infinity, P n equal to 1, and we have to get it as e power minus rho. Let us see that now. To find P naught, we use the normalizing condition sigma n equal to 0 to infinity, P n is equal to 1, where P n is given by P naught rho power n by n factorial, where n equal to 0, 1, 2, 3 and so on. This is rewritten as, after plugging in the expression for P n, P naught times rho power n by n factorial. Now, P naught is independent of the summation variable, so can be taken out, and we have when you supply the value n equal to 0, it becomes rho power 0 by 0 factorial, which is 1, plus n equal to 1, it becomes rho by 1 factorial, plus n equal to 2, it becomes rho square by 2 factorial, and so on to infinity. We have this is equal to 1, the normalizing condition. So, now you see that the expression inside the bracket, which is of the form 1 plus x by 1 factorial plus x square by 2 factorial and so on to infinity. This resembles the expression or the summation of e power x. So, we write this as, this implies that p naught times e power rho is equal to 1. In other words, we have p naught equal to e power minus rho. Now, substitute this expression in the expression for Pn. Now, we have Pn equal to e power minus rho, rho power n by n factorial. We have the values of n starting from 0, 1, 2, 3 and so on. So, this is the expression for finding the steady state probability of finding n customers in the system in the steady state for the infinite server Markovian queuing model. Our next aim would be to obtain the performance measures for this model. Let us look into it now. The performance measures are given by Ls equal to sigma n equal to 0 to infinity n into Pn, but that is to be obtained as rho. We will see that now shortly, and then Lq is 0. Ls here is the, on an average, it is the expected number of customers in the system in the steady state. So, that is nothing but given by rho. Lq is the expected number of customers waiting in the queue, that is 0. Why? Can you think of the answer? We are dealing with a infinite server queuing model. So, every customer, he or she is the server himself or herself. So, there is no waiting time for the service. It is a self-service queuing model. So, there cannot be any waiting time in the queue. So, whatever the time to be spent in the system, it will pertain to only the service time. So, this necessitates that Lq to be 0, and we do get that Lq is 0. And we have Ws, waiting time in the steady state of a customer in the system, that is given by Ls by lambda, where Ls is to be obtained as rho. So, it would be Ws is Ls, which is rho divided by lambda. Now, once you have that there is no customer waiting in the queue and there is no waiting time for a newly arriving customer in the system, only it is for the service, not in the queue. So, then if Lq is 0, it makes sense that Wq, which is Lq by lambda, also is 0. So, it is only Ls out of the performance measures. We have non-zero performance measures to be Ls and Ws. Ls is rho, the parameter of the distribution, namely rho Pn, and Lq is 0, Wq is 0. Because Ws is Ls by lambda, we have Ws to be written as rho by lambda. Let us see the derivation of Ls to be rho next. So, we have Pn, we obtained it as e power minus rho, rho power n by n factorial, where n equal to 0, 1, 2 and so on to infinity. What we require now is Ls. Ls is defined as seen earlier, sigma n equal to 0 to infinity n times Pn, right. Now, we substitute for Pn. So, it becomes sigma n equal to 0 to infinity n into e power minus rho, rho power n by n factorial. This further becomes e power minus rho can be taken out, because it is independent of the summation variable. We have sigma n equal to 0 to infinity n into rho power n by n factorial, but when you cancel out n and n factorial, I get this as 1 by n minus 1 factorial. So, to be able to see this as a exponential series, we have sigma n equal to 0 to infinity rho power n minus 1 plus 1 by n minus 1 factorial. I am adding and subtracting 1 to n in the power of rho into e power minus rho is already there. Now, this further becomes e power minus rho times, in this expression rho power n minus 1 plus 1, I will remove this rho power 1 out and club it with e power minus rho. So, I get rho times e power minus rho sigma n equal to 0 to infinity rho power n minus 1 by n minus 1 factorial. When I supply values for n here starting from 1, because when I put n equal to 0, it becomes minus 1 factorial, which is not defined. So, we write this as summation n equal to 1 to infinity, supply the values. We already have rho into e power minus rho, and start with n equal to 1, it is rho power 0 by 0 factorial, which gives you 1, plus second term is rho power 2 minus 1, which is rho power 1 by 1 factorial, plus rho square by 2 factorial, and so on to infinity. Once again we see this is the summation e power rho. So, when you substitute e power rho here, we get Ls equal to rho into e power minus rho times e power rho. So, e power minus rho, e power rho get cancelled. So, we end up with Ls being rho. So, this is what we had to get, and the expression tallies. Now, to get Ws, we use the Little's formula. So, we have Ws equal to rho by lambda. When I substitute rho as lambda by mu divided by lambda, I end up with 1 by mu. So, Ws is 1 by mu, Ls is rho. So, these are the two non-zero performance measures we have for this infinite server model, queuing model, and we have Wq, prior to that Lq, the two performance measures to be 0. So, we obtained the performance measures as follows: Ls is rho, Lq is 0, Ws is rho by lambda, which is nothing but 1 by mu, because rho is lambda by mu, and Wq equal to 0. Next, we will see the examples for this model. Students are accepted into a correspondence course in an electrical wiring as soon as they register, and they then complete the course at their own pace. The completion times seem to follow an exponential distribution with a mean of 7 weeks. New enrollments to the course follow a Poisson process with a mean rate of 50 per week. The questions are: determine the number of students that are expected to be concurrently enrolled in the course, and B, the probability that it will take a student more than 7 weeks to complete the course. Let us look into the data given here. Students are accepted into a correspondence course in the branch of electrical wiring as soon as they register. They then complete the course at their own pace. So, the completion time is the service time. So, that is not fixed, it is random. They complete the course at their own pace. So, it varies from student to student, the time for service, that is the time for completion of the course that they have registered. The completion times seem to follow an exponential distribution with a mean of 7 weeks. So, the completion times again meaning here the service time with respect to the theory that we have seen. So, to follow an exponential distribution, that means the departures are Poisson. So, we have the information given that the service times are Markovian, namely exponential, and so the second index corresponds to the Markovian departures. But once you have the service times to be exponential, the parameter should be given, namely mu. But information about mu has been given here in terms of the mean time. So, let us look into that. It is the mean of 7 weeks. So, the units are in terms of weeks. New enrollments to the course follow a Poisson process. So, new enrollments to the course meaning the arrivals, new arrivals are occurring according to a Poisson fashion. Now, again the rate should be mentioned here, information about lambda. So, the mean rate is given by 50 per week. So, you see the difference as regards the service, it is the information given to us is in terms of the mean time. So, it is 7 weeks, whereas as regards the arrival rate, instead of giving you the mean time, the information given to us is in terms of the mean rate, that has been given as 50 per week, and mu is 1 by mu is 7 weeks. So, mu is 1 by 7 per week. So, what is rho then? Rho is lambda by mu. So, you would get it as 50 divided by 1 by 7. So, rho you get it as 350 units. Units actually gets cancelled here. Now, we have the first question to be the number of students that are expected to be concurrently enrolled in the course. So, this is nothing but the question is about the LS. So, which is nothing but rho, we already found out theoretically. So, but rho in this case is 50 by 1 by 7, which comes to 350. So, the answer for the first part is 350. The second question is probability that it will take a student more than 7 weeks to complete the course. So, this part I leave it to you. The answer of course is here. You have to find the probability that it will take a student more than 7 weeks to complete the course. So, the probability you have to calculate is that of the time. Time is the service time, that is more than 7 weeks. So, which is the probability you would use? Distribution, it is corresponding to the exponential. So, you have to find the survival probability of say x service time is greater than 7. So, that is nothing but integral 7 to infinity, and the parameter for the service time mu is 1 by 7. So, the parameter is 1 by 7, the PDF would be e power minus 1 by 7 into x into 1 by 7 dx integral 7 to infinity, because the question asked is more than 7 weeks. So, you try this part, the answer you should get it is 0.368. The next example, problems arrive at a computing center in a Poisson fashion at an average rate of 5 per day. So, the information about arrivals has been given in this first sentence. So, problems are the arrivals, they arrive at a Poisson fashion and the rate is given to be 5 per day. So, lambda has been directly given to you as 5 per day, unit of time with respect to the arrival rate is day. The rules of the computing center are that any man waiting to get his problem solved must aid the man whose problem is being solved. If the time to solve a problem with one man has an exponential distribution with mean time of 1 by 3 days, mean time is 1/3 of a day. So, which means that 1 by mu has been given as 1 by 3. So, mu is 1 by 3. So, it will be 3 per day. And if the average solving time is inversely proportional to the number of people working on the problem, approximate the expected time in the center for a person entering the line. So, the first half gives you the information about the arrivals and the service times. Both the rates have been given to you. So, we see that as the number of people working on the problem increases, the rates also increase. So, this is the observation we made when we today after the introduction, that when we commented on the infinite server queuing model. So, this is nothing but an example of the infinite server queuing model. So, we use the Pn to be equal to e power minus rho power n by n factorial, where n can be starting from 0, 1, 2, 3 onwards. The question asked is here, what is the approximately the expected time in the center for a person entering the line. So, for a new arrival, it is asked that the expected time in the system. So, which is again Ws, which is asked indirectly, but we know that Ls is rho. So, Ws will be Ls by lambda. So, it will be 1 by mu actually. So, let us see this part. So, we have the information given to us as lambda is 5 per day and mu is 3 per day. The service rate increases with increase in the number of persons. So, we have mu n is directly proportional to mu. So, mu n is written as n times mu. So, this goes with as n increases, the mu n, namely the service rate does increase. So, when there are n problems in the system, then we have Pn equal to e power minus rho power n by n factorial. N can be from 0, 1, 2, 3 etc. So, that Ls is equal to rho. So, which is nothing but 5 by 3, 1.67, and Ws is given by Ls by lambda, which is 0.4 days or 9.6 hours. We have